Hello and welcome to parametric equations and parametric equations as they relate to calculus. This is just meant to be a nice quick refresher on what you've already learned from parametric equations in precalculus, and then how to apply the basics of them for calculus, which will enable you to do your work that you need to get done today. So we're looking at 10.1 in our new textbook. Parametric equations, just as a refresher, use a parameter, generally we use t, in their definition. So x and y are both going to be defined in terms of t instead of y being defined as a function of x. This allows for us to have a coordinate at a point in time. So it gives us extra information that we wouldn't have had if we just have x and y. That also allows us to calculate speed and direction, which is going to be related to vectors momentarily. Refresher problem from precalculus, you might see something that looks like x of t equals 2 minus t squared, and y of t equals t plus 3. I could ask you to graph this, for instance, on the domain 0 is less than or equal to t is less than or equal to 3, or to describe the curve that this creates. I could ask you to eliminate the parameter. Hopefully these words are resonating and you're remembering them. If I wanted to graph this, I would make a txy table, and I would say, well, t can equal 0, 1, 2, 3. And then I'll just fill out what x and y would equal. So x would equal 2, and then x would equal 1, and then x would equal -2, and then x would equal -7, and y would equal 3, 4, 5, 6. So when I graph the path, I'm going to be graphing the xy points. So t does not by default show up in the graph. I would graph the point 2, 3, and then 1, 4, and then -2, 5, and -7, 6. And I would see that that's what the path would look like. If I want to show where t is, I always encourage my students to really write like small, just t equals 0, 1, 2, t equals 3. You don't necessarily have to do that for every value that you have, but that will show you then the direction that the particle or whatever is traveling. We also could then talk about, is this speeding up or slowing down? And how do you know? Etc. To eliminate the parameter means to get rid of t and write this in just Cartesian form with x and y. So to eliminate the parameter, I would solve one of these equations for t, whichever one is easiest. So I would say t equals y minus 3. And then I'm going to substitute that into the other equation. So I get x equals 2 minus y minus 3 quantity squared. That would eliminate the parameter. And so now I just have x in terms of y, or you could do it vice versa and have y in terms of x. This may allow you to graph it easier. However, you lose that bit of information about t when you eliminate the parameter. So if you're given parametric equations, we want to generally keep them as parametric equations. To graph these on your calculator, just a reminder, you would change your mode to parametric, and then when you hit the y equals, you'll have x1 of t and y1 of t. And when you go to set your window, make sure that you note what your t step is. If your t step is bigger, then it will graph faster with less quality. So if you want a higher quality, then you would make your t step smaller. That's just a little refresher from precalculus. Now, if we were going to do some calculus with this, we need to be able to take a derivative, so we need to find dy dx. If x and y are their own separate functions of t, then the slope of a curve at the point xy would simply be given by dx or dy dt over dx dt. Algebraically, it looks like I'm just dividing the numerator and denominator by dt. You know that that's not what is actually happening, because that just means with respect to t. We're not dividing by anything. But the algebra holds, so if that's the way you want to think of it, that's fine. Dx dt can't be 0 just because you're not allowed to divide by 0. So with the example that I had just looked at, we said that x was 2 minus t squared and that y was t plus 3. So if I wanted dy dx, I would say, well, that's dy dt over dx dt. dy dt is 1. Dx dt is negative 2t. Notice that this gives us dy dx, which is the slope, right, the rate of change of y over the rate of change, or the change in y over the change in x. So it's the slope on the xy plane, but it gives it to us in terms of t, which is the parameter, so that at any time I would know what the xy slope is, which is kind of interesting. It makes it even more interesting then when you would go to find the second derivative. So the second derivative, it would be the derivative with, I want to find the derivative with respect to x of the first derivative, which is dy dx. And we know this notation, we call this d squared y over dx squared for the second derivative. Well, the trouble is that I have dy dx as a function of t. So if we think of this, and I'm just going to rename it for a second, I'm going to call it u, which is a function of t. But I want to take the derivative with respect to x. So this is going to invoke the chain rule. So I would be taking the derivative with respect to x of that function, right, u of t, but then I would have to multiply that by dt dx, or to make this notation better, I would say du dt, because u is a function of t, and then times dt dx. Again, if you think about the algebra of this, you could say, oh, look, the dt's cross out, and you get du dx, which is what I would want here, right? Du dx. And that is an incorrect, really, way to think about it, but it works if that's what helps you remember that. But the thing is, I don't have the derivative of t with respect to x, but I can take the derivative of x with respect to t. In fact, I already have done that. So it turns out that this would be du, which was the first derivative, dt, divided by another dx dt. So that means that that's dy dx, which was dy dt over dx dt. And then I'm going to take the derivative of that with respect to t, because that's the variable that I have. And then I'm going to divide by another dx dt. If you didn't get that conceptually, sorry, that's probably my poor explanation of it. It's okay. You can just memorize the formula. So here's the formula. The second derivative here is that you're taking the derivative of your first derivative with respect to t, and then just remember, you have to divide by another dx dt at the bottom. I don't know that you would ever be asked to find a third derivative, but if you were, then it would be the same thing. You would take the derivative with respect to t of the second derivative, and then you would have to divide by dx dt again. So in our example that I was showing you, we had dy dx was, let's go back up and see what that was, 1 over negative 2t. So then if I wanted the second derivative here, I would take the derivative of the first derivative. So d squared y over dx squared would equal. This is negative 1/2 t to the negative first power. So that would become positive 1/2 t to the negative second power. 1 over 2 t squared. However, that doesn't account for the fact that the chain rule part, so I need to divide by dx dt. Well, what was dx dt? I already found dx dt from the first problem, that dx dt was negative 2t. So now d squared y over dx squared, which is the second derivative, is now going to equal, if I simplify this, 1 divided by negative 4t cubed. Hope that kind of makes sense. So now you understand parametric equations and how to take derivatives and second derivatives parametrically. Sometimes you may see the parametric equations written as a vector, just FYI on that. So for the original function that I had, x was 2 minus t squared, and y equaled t plus 3. You may see it written like that in some occasions for the original xy. Don't be concerned with that. That's fine. We're going to talk more about that tomorrow. Okay, so 2 things left. One is to find all the points of horizontal and vertical tangency. We're not going to do this problem. I'm going to leave you to it. But if we want a horizontal tangent to a curve, we know that that means that the slope, dy dx, has to equal 0. And so if dy dx equals 0, then that means the numerator of this thing equals 0. So dy dt equaling 0 is what's going to give us a horizontal tangent. However, since parametric curves are not restricted to passing a vertical line test, if I wanted a vertical point of tangency here, then I would say, oh, well, that means the slope is undefined, which means if dy dt over dx dt is undefined, then that means the denominator of that, which is dx dt, equals 0. So if you're asked to find a vertical tangent, you set dx dt equal to 0. If you're asked to find a horizontal tangent, you set dy dt equal to 0. There are some cases, if you're not looking at continuous smooth functions that are differentiable everywhere, that would change, but for what you need to do right now, that's fine. Last but not least, we have the arc length formula. The formula for arc length, which Sharif taught you, is that the arc length is the integral from a to b of the square root of 1 plus h prime of x quantity squared dx. The rationale was based on the Pythagorean theorem. This is going to be the same if I want to find the length from here to here. Then I can look at it and I can say, well, if this is a little bit of change in x and this is a little bit of change in y, then the arc length, this is what Sharif did with you, then the arc length would be the square root, or the length of the hypotenuse here, would be the square root of dx squared plus dy squared. But I would have to add all those up, so I would need an integral. So, and in this case, I've got parametric equations. So I'm just going to say, well, let's divide everything here by dt quantity squared and dt squared there as well. And let's just make it the square root of the whole thing. In doing so, I've multiplied by 1 over the square root of dt squared. So I've multiplied by 1 over dt. So to compensate for that, I've got to multiply by dt over on the right. And that ends up working out just fine, because when I add them all up by integrating, then I'm going to need that dt there. Again, I hope that you understand conceptually the way that works, because it makes your life easier. But if not, you can just memorize the formula, that this would be the arc length formula parametrically. So you can do the problems on your worksheet. Good luck. Have fun. I'll see you tomorrow.